Welcome back, class. In the last section of Test 4, we're going to talk about graphs of the derivative. And so I'm going to start with an example of something that we've done before. Namely, that in the first video of section 3.3, we showed that if you started with the function x squared minus 6x plus 12, and you calculated its derivative, that you would get 2x minus 6. So what I want to do now is I want to look at a graph of both of these on the same pair of axes and try and decide what the relationship is between the graphs. So we know, before I even show it to you, the graph of the red function is going to be a parabola. The graph of the blue function is going to be a line. Okay, and remember, the red is the original function, and the blue is the derivative. So this might take a minute to sort of sink in and try and figure out what is the relationship between these two graphs. So to start, I want to stress the blue graph is the derivative of the red graph, which means that at every point, the blue function is telling you the slope of the tangent line to the graph of the red function at the same input. I think that's actually clearest at this point here that I've circled. Here, if you imagine drawing in a tangent line to the red graph, that tangent line is horizontal. And a horizontal line has a zero slope. So a point where the tangent line is horizontal always corresponds to a spot where the derivative is 0. This observation is going to be critical for a great deal of what we're going to do for the rest of this semester. In particular, for this graph, I want you to note this spot on the red graph where the tangent line is horizontal corresponds to this point on the blue graph where the blue graph takes the value 0. That is to say, where the blue graph crosses the x-axis. So to repeat, this spot on the red graph, where the tangent line is horizontal, corresponds to this point on the blue graph, where the derivative is 0, which I can see because the graph of the derivative crosses the x-axis. But it's important to note the relationship between the red graph and the blue graph doesn't only exist when the derivative is 0. For example, here's another point on the red graph, and I want you to imagine what the tangent line would look like there. And one thing you'll see in your mind as you think about this is that that tangent line has negative slope, which tells me that at this point, the derivative is negative. Again, you can see that if I look at the corresponding point on the blue graph below. So, negative sloped tangent line on the red graph corresponds to a point on the blue graph where the y-coordinate is negative. So, negative slope on red graph corresponds to a point on the blue graph that is below the x-axis. If instead I look at a point over here, we can imagine the tangent line here. That tangent line has positive slope. And so that positive slope tells us that the derivative is positive, which tells us that the corresponding point on the blue graph should be above the x-axis. So at every point on the red graph, if I look immediately below it to the blue graph, the y-coordinate of that point tells me the slope of the red graph at that point. Be that a positive slope, a negative slope, or a 0 slope. But where the derivative is positive and where the derivative is negative is not the only information that I can read off of the blue graph. So now, I want to actually look at these 2 points. What's true at these points? Well, picture the tangent lines. Both of those tangent lines have positive slope, which means that if I look down at the blue graph below these 2 points, I'll see both of them have a positive y-coordinate. Both of them are above the x-axis. But if you picture the 2 tangent lines simultaneously, you'll notice that the point on the right actually corresponds to a steeper tangent line than the one on the left. Meaning that although the slope at both of these points is positive, the slope at the right point is actually larger than the slope at the left point. If you look down at the blue graph below, you'll see that this is also reflected in the blue graph. The y-coordinate of the right point on the blue graph is larger than the y-coordinate of the left point on the blue graph. And so, what does this say? This says bigger y values on the blue graph, that is, the graph of the derivative, correspond to steeper points on the original red graph. So, large value on the derivative graph means large derivative, which means the original graph should be steep. And so if you look holistically at the red graph, you'll see that if I start on the left, the tangent line has a very steep negative slope. But as I move slowly to the right, that slope gets shallower, still negative, until we hit the vertex of the parabola, at which point the tangent line now goes from having a slightly negative slope to a zero slope. And then as I continue moving to the right, that tangent line will then have a slightly positive slope to a very positive slope. And so what I've just described is, as I read from left to right, the derivative starts off negative, then becomes less negative, then becomes zero, then becomes slightly positive, and then becomes more positive. And so that story about the red graph is reflected in the fact that the blue graph starts off very negative, becomes slightly less negative, then becomes zero, then becomes slightly positive, then becomes more positive. Here's another pair where I have graphed some function, it doesn't matter what function, in red, and I've graphed the derivative of this function in blue. I again want to make sure that while looking at this graph, I can understand the relationship between the red graph and the blue graph. Again, every point on the blue graph tells me the slope of the red graph at the corresponding point. When trying to make sense of these things, I recommend always first identify the points on the original graph where the derivative is zero. These are the points on the red graph where the tangent line is horizontal. So these are the spots on the red graph where the derivative is zero. Those horizontal tangent lines on the red graph correspond to these x-intercepts on the blue graph. Now, I want you to think about the question, where is the derivative of the red function negative? Well, if I look at the red graph, then the derivative is negative wherever the slope of the tangent line is negative. I've circled a couple such points on the graph. These are two spots where the slope of the tangent line to the graph is negative, and hence the derivative is negative. On the other hand, at the two spots I've circled now, the slope of the tangent line is positive, and so the derivative is positive. So where is the derivative negative? Well, the derivative is negative during this sort of downward slope part in the middle of the graph. So, in other words, the answer to this question is that the derivative is negative between the 2 points that I have circled here, and it's positive everywhere else. Now, notably, the 2 points I've circled are exactly the 2 points where the derivative is zero. That is something we'll talk about a lot later. But for now, I want to point out there's another way we could have answered this question. Namely, we could have answered this question by looking at the blue graph instead. The blue graph literally is a graph of the derivative, so if I want to know when the derivative is negative, I could have just looked at the blue graph and seen when the blue graph is negative. And that's a little easier to read because negative, rather than negative slope, just means that the point on the blue graph is below the x-axis. So the derivative is negative in this range on the blue graph. And so the answer on the blue graph is that the derivative is negative between these 2 points, between the 2 x-intercepts that we talked about before. Note, this agrees completely with the answer we got when we looked at the red graph. I want to look at one more thing. Namely, I want to look at the vertex of this parabola. This vertex of the parabola is on the blue graph. And so that's saying that this is the point where the derivative is the smallest. And so my question is, what does that look like in the original red graph, the point where the derivative is smallest? What that looks like is it looks like the corresponding spot in the red graph is the spot where the function is decreasing the fastest. That is, the negative slope is the steepest. Now, I should note, it's pure coincidence that the graphs cross at this point. That has no significance at all. But you can see in the red graph, this is the steepest negative point on the red graph. If I look over here on the left at these points and imagine the tangent line, that tangent line has shallower slope than the slope of the tangent line at this other point that I've highlighted. And the same is true at these points over here on the right. And so the fancy name for what's happening here at this circled point on the red graph is an inflection point. That is, a spot where the direction of the change changes. So up until this point, the function is decreasing faster and faster, and after this point, the function is decreasing slower and slower. So really, you can read a lot of information about a function out of the graph of its derivative. And all of that information is talking to you about how the function's changing. That is, what the slope of the original graph is, or what the slope of the tangent line is, whichever way you want to think about it. I'm going to show you one more pair of graphs. This time I've used orange and purple. One of these is the function, and the other is the derivative of that function. Using just what we've talked about in terms of how the function's graph corresponds to the derivative's graph, I want you to take a moment, pause the video, look at this graph, and tell me, is the orange function the original function, or is the purple the original function? And then I'm also asking effectively, is the orange function the derivative, or is the purple function the derivative? Okay, so let's talk about how to think about this. Okay. If you think back to our discussion, the first thing I emphasized was that it's really easy to tell from the original graph where the derivative is 0, because it's those spots where the tangent line would be horizontal. And so it's a natural thing when presented with this question to look at where the tangent lines to one of the graphs are horizontal and see whether the other graph is 0 there or not. So here, for example, I have circled for you a spot on the purple graph where the tangent line is horizontal. That is, at this point, the derivative to the purple graph is 0. I look over here now at the orange graph, and I see the orange graph, in fact, is 0 at that point, which might make me inclined to think, oh, okay, so the purple graph is the original function, and the orange graph is the derivative. But hold on. Here's a spot now where the derivative of the orange graph should be 0, because the tangent line is horizontal there. But if you now look at the corresponding point on the purple graph, well, the purple graph is 0 there. And so that would be consistent with the orange graph being the original function and the purple graph being the derivative. In fact, we can't actually determine the answer just by looking at the places where the derivatives of either of these things is 0. I have to look a little more closely here. So namely, what I want to do is I want to look at a pair of points like this one, and I want to think about what would be true about the derivative of the orange function and the derivative of the purple function at these points. At this point, the derivative of the purple function, well, that's saying the slope of the tangent line, and that tangent line has positive slope. So at this point on the purple function, the derivative of the purple function should be positive. If you then look at the orange function, its value is in fact positive. Okay. That would be consistent with the purple function being the original function and the orange one being the graph of the derivative. But could it be the other way around? Well, to decide that, I have to now look at the orange function, and I have to think, okay, at this point on the orange graph, is the derivative supposed to be positive or negative? And at this point, the tangent line has positive slope, and so the derivative of the orange function at this point should be positive. But if I look at the corresponding value on the purple function, there, that value is negative. And that tells me that the purple function can't be the derivative of the orange function. Let me summarize all of that again in a table here. We're really at both of these points looking at two pieces of information. Whether the function's value is positive or negative, and whether the slope of the tangent line to the function at that point is positive or negative. In the case of the orange graph, both the y value and the slope are positive. In the case of the purple graph, the value is negative, but the slope is positive. And so, if the purple function was the derivative of the orange function, the value of the purple function would match the slope of the orange function. That is to say, again, if the purple function is the derivative of the orange function, then the slope of the orange function should match the value of the purple function. But they don't. And so because these are different, it can't be the case that the orange is the original function and the purple is the derivative. Now, if instead purple is the original function, then we would expect the slope of the purple function to match the value of the orange function, and hooray, it does. So our conclusion then is that purple is the original function, and then orange is the derivative. That's all for now. In the next video, we're going to talk about how to sketch a graph of the derivative if I give you a graph of the original function. So long for now. I'll see you next time.